Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously, we started visualizing the 3D geometry that we got from Content Tools, the last step of which was being able to move the camera around the object. So today I'm going to add this functionality to the geometry viewer, but first I'm going to briefly explain a bit about spherical coordinates, which we'll be using for the camera movement. Until now, we have been using a coordinate system that's called the Cartesian coordinate system, and it's one of the simplest coordinate systems. Each point in a three-dimensional space is described by three numbers, x, y, and z, and those numbers describe the position of this point with respect to a point that is the origin. But there are, of course, other coordinate systems, and one of them that's used very often in game development is called the spherical coordinate system. And we can use that to describe the same point with respect to the same origin using a set of three different numbers. Here we have the same point, P, and it can be described with respect to the same point origin with two angles and the value of R, which is the distance of P to the origin. And since using a different coordinate system doesn't matter for the position of a point with respect to the origin, there is always a way to transform between the Cartesian coordinate system and the spherical coordinate system. And in case that z-axis points upwards, we can derive these equations. So as you can see, R is just a good old Pythagorean formula for the length of the vector. And using basic trigonometry, we can also derive these two. And in case that we also want to go the other way around, from spherical coordinate system to the Cartesian coordinate system, we have the reverse of these formula. So putting the value of theta and phi in this formula and using the diameter of this sphere, we can compute the value of x, y, and z. So this formula holds for the Cartesian coordinate system when the z-axis is the vertical one and x-y axis are on the horizontal plane. But because we are using a right-handed coordinate system where y points upwards and z is coming out of the screen, you can see that the y and z axis are switched here. So where we have a z-axis, there is a y-axis, and where we have a y-axis, we have a z-axis in the opposite direction. So we can use this formula still, but we need to switch z with y and y with minus z. And when we do that, we get to the formula for our right-handed Cartesian coordinate system. Here you can see that y and z axes are switched, and z has the opposite sign because it's going to the opposite direction. Why I am explaining all of this has to do with the way that I want to move the camera around the object. So as you might have guessed, the spherical coordinate system is a perfect system to use for moving around an object. And that's the way I want to move the camera. So here is the camera, and it will be looking at the center of the object that we have. And we can just tilt the camera up and down and around the object. I would also like to be able to move the camera in the vertical direction, like this. In case we have some kind of elongated object that we want to inspect on different heights, it would make sense to have the ability to move the camera's target in the vertical direction as well. So now that we know how to convert between Cartesian coordinate systems and spherical coordinate systems, let's go to our code and implement the camera movement around the object. Okay, now we need to write MoveCamera function here. Since the camera position is a point and we want to do vector calculations, I'm creating a vector and we are going to compute the spherical coordinates using the camera position. This is really simple. I just wrote out the formula that I explained before. Luckily, we have all the functions that we need here in the math class. So we can just calculate the value of r, theta, and phi. And then we are going to change those numbers depending on how much the mouse was moved. And that way we can just rotate the camera around the origin. Okay, again, we scale the amount of movement in pixels by a value that works for us. So this has been determined empirically by just trying out different values and see if the camera movement is not too fast or too slow. And the value of r is what determines how close we are to the object itself. And I would like to set that by using the mouse wheel. Going back to look at the spherical coordinates again for a minute. Here we can see that phi goes all the way around from 0 to 2p. Theta, however, goes from 0 to p. And that's to make sure that each point on this sphere is described by a unique set of coordinates. And to do that in code, I just clamped the value of theta between 0 and p. I'm not clamping to exact values here because the camera's up vector is undefined when theta is exactly 0 or exactly p. So I'm clamping to a value that's really close to 0 and p. By the way, feel free to let me know if you prefer pi over p because I'm saying p all the time. Now that we moved the camera using these coordinates, we should set its position again in the Cartesian coordinate system. And that means that we need to convert back from the spherical to Cartesian coordinate system. And we finally set the camera position according to these new coordinates. And that's all this function does. So let's go back and implement the rest of these event handlers. So we did mouse left button down, mouse move, and mouse left button up. Next one is mouse wheel, and that one will be the zoom in and out interaction. This one is really simple. The camera isn't moving around the object, but only the distance between the camera and object is changed by taking the sign of this e.delta, which indicates in which direction we scrolled the mouse wheel and by how much. And by just taking the sign of it, we account for the direction that the mouse wheel was scrolled. So if we scroll up, then we zoom in, and when we scroll down, we zoom out. Next is when we click the right mouse button. Here again, we remember where the user clicked and also that the right mouse button is down. And we already have the mouse move event for when the right mouse button is down. So we only need to do the last one here, which is when the user releases the right mouse button. Again, we only release the capture if the left mouse button is not down. And if I did everything correctly, this is all we need to do to rotate the camera around the object. So now I'm going to hold the mouse button down and drag the mouse. And you can see that although it works, it's kind of unstable. I think I have made a typo somewhere. Let's try and fix this. Here I made a mistake. It should be camera position. After each time that we call this function, we are going to calculate the amount of mouse movement with respect to the last movement. And that means that we need to update clicked position. And that's what I forgot to do. I think that was the cause of our problem with rotating around the object. So if I would go ahead and update the clicked position and set it to the current position of the mouse, then I think the problem would be solved. Yeah, as you can see now, the movement is much more fluent. We can go around the object like this, and I can move the target of the camera. So the camera moves up and down. And I can zoom in and out as well. Here you can see the position of the camera, and from this we can deduce the direction of the axis. So now that we can move around the object, we basically checked everything that we can to see if the object is generated correctly. Right now we only can check whether the width and length of the object is set correctly. But I'd also like to see if our generated UV coordinates are correct. And therefore I'm going to use a texture for this to display an image over this plane. And if our UV coordinates would be wrong, then you would see deformations on that image. And that way I can test the correctness of the UV coordinates. Okay, let's use a texture for the plane. I'm going to put an image in our resources. We don't have a resource folder yet. I'm going to create a new folder and call it resource. And in here, I'm going to create another folder for primitive mesh view. And I'm going to just drop an image in here that I'm going to use for the plane texture. And using this new texture is pretty straightforward. Let's delete this. Every time we add a new resource, we need to also set build action for it. So it will be used as a resource. And then I'm going to load this texture when we open the primitive mesh dialog. So here I'm going to have a static constructor. And in here, I'll just call a function that loads textures. And we have load textures because we'll have more textures than just this one. We'll have other textures for other primitive meshes that we can also load. Here I'm just getting the URI for this resource, which is at this address. And I would like to load this resource into an image brush together with any other textures that we are going to load. So I'm going to have a list of image brushes. And when we load the textures, I'm going to just put those in here. First clear all the textures that we might have. And then for each of our URIs, I'm going to create an image brush. Okay, here I'm just getting a stream for all the resources that are packed into this application. And in that stream, for this URI, I'll read all the bytes of this resource. So basically, it's just a binary read from data within the application. And when we have this data, we can convert it to a bitmap source. And from that, we can create an image brush. Here I'm transforming the scale of the brush to flip it upside down, because in WPF the direction of the UVs are in the opposite direction. I have to flip the direction of the V axis. And therefore I'm using this scale transform, which basically flips the V direction and uses the center of the object to do that. And we also need to set the viewbox units to absolute, because otherwise the renderer would rescale the UV coordinates in such a way that it would always fit within 0 and 1. And when we want to use a subsection of the UV coordinates, then that wouldn't be possible, because it would automatically scale our object to fit to 0 and 1. Now we can use this texture for the primitive meshes that we have. And I'd like to be able to toggle the texture on and off, so I can see the geometry itself and the textured version of it. And therefore I'm going to add a checkbox next to this combo box. And here in this event handler, I'll just check which primitive type we are displaying and then pick the right texture for that. Now that we have the texture for this particular primitive type, I am going to use it for the diffuse material, and that way we can make this object textured. Again, that's not exactly what I was expecting to see, so let's see what's going wrong here. Okay, first of all, we need to set this texture when we create such a geometry. So here I'm going to set the texture as well. And while we are here, I'm going to disable selection of these type of primitive meshes, because otherwise the application will crash because we haven't implemented the functions for these. So we just return if any of these are selected. I think the problem now is that our resource is not loaded correctly and we get a black texture. I think this will fix the problem and also display the texture. There you go. We have our textured plane and we can zoom in and out. So apparently the UV coordinates are right. I don't see any deformation or stretching here. However, I can't really check if our segmentation works. And like I said before, there is no way of displaying a mesh in wireframe in WPF. So I need to do something myself to check if our segmentation is working. I can do something temporary, and that's to use the entire range of UVs for each segment. So we can basically put this texture into each segment. And when we increase the segments, then we see a repetition of this texture. So let's do that to check if the segmentation works. Here in Primitive Mesh, where we generate our UV coordinates, I'm going to temporarily comment out these and then just use a range between 0 and 1 for each segment. In this way, we just toggle the values that are added to the X and Y components of the UV coordinates between 0 and 1. And in that way, we use the entire range of the UV coordinates. So now if I would increase the segmentation, then you can see that the texture will repeat. And they are mirrored and flipped because this equation isn't really correct for each segment. It causes the UV coordinates to alternate between 0 and 1, which will flip and mirror the UVs in each segment. But other than that, I see that the segmentation works as intended. Here we have 10 segments by 10 segments. And that's great. Let's put this back to normal. And this concludes what I wanted to do to visualize the primitive meshes. And next time I'm going to carry on and try and save our geometry assets to an asset file. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!